So really here all we're doing is we're applying our definitions and our theorems, and we're solving for our unknown values. In this case we've got x. So I've got a situation here. So chords that are equidistant to the center are congruent to each other. So that's going to come in handy here. So we've got chords that are equidistant from the center because they're both a length of 5 from the center of the circle. That's going to make this yellow chord congruent to this yellow chord. So if we can find the length of 1, we'll be able to find the value of x. So I'm going to come over here. Well, we've got this perpendicular happening. That's going to make this perpendicular because they're congruent and they're equidistant. So we've got 7 and then we've got 7. That's a length of 14. So x is equal to 14. Let's see if we can apply this rule anywhere else. Here we've got a portion of a diameter, right? Perpendicular to a chord, and perpendicular to 2 chords right there. Here we go. We were equidistant. So that's 2. That's going to make this green segment 2. So x is equal to 2. And the reason I know this is because we've got 5 over here, 5 over here. We had congruent chords, therefore we had congruent arcs, making all of these arcs the same. We also had congruent segments, which would make all of those segments the same. So we had lots of similarity stuff there, but congruent, not just similar, congruent. It looked similar, but it was actually equal to each other. So the chords are congruent, therefore x equals 2. Here we are again. We've got some congruent distance going on. They're equidistant. The reason I know this is because this chord is going to end up being congruent to this chord because this is given to us as 10, and we know that the chord is bisected, so this is 10, and this segment down here is congruent to this segment on the left, so it's 10, and it's being bisected, so it's 10. Let me go through that again. These 2 congruent segments are important because it links one chord to the other chord. The other thing that we have going on here is the fact that we've got that perpendicular, which is going to bisect the chords. So now 10 is congruent to this 10, which links to this 10, and this chord on the left is also bisected, so that's 10, which means that x has to be 7. So the chords are equidistant to the center, they're going to be congruent chords. So when the chords are equidistant to the center, they are congruent to each other. So if we can determine that they're congruent to each other, we know that they're equidistant. So let's go back to that one. We knew that they were congruent to each other because we had 5 and 5. Therefore, they had to be equidistant. Okay, let's see what we have here. Here we go again. We've got equidistant to the center. That means the 2 chords have to be congruent. So the chord on the left is going to be a length of 25 plus 25, which is 50. So x equals 50. And in this next problem, and any of these problems, hopefully you're pressing pause and saying, let me try, let me try. What do we have here? we have a diameter, right? That's 20. We have 2 radii, and radii are all congruent, so that makes this 10 and this radius 10. And we need to find x, and we've got perpendicular right here. So when we've got that perpendicular, we've got the chord being bisected. So if the whole chord is 16, half of it is 8. We've got a right triangle here, and we have a 6, 8, 10. There's that Pythagorean triple again. X equals 6. The more you know those Pythagorean triples, the better off you're going to be. They love using those Pythagorean triples here. Okay, in the next video, we're going to finish it off with these 4. You definitely might need a calculator on this first one right here. After that, we're going non-calculator on the rest.